Compared to a digital photo, a short video animation often gives a greater sense of presence. However, creating a nice video loop is difficult when there are many moving elements in the scene. Previous work involves user guidance to segment a complex scene into separate looping regions. We design an optimization algorithm to analyze a short input video and automatically segment it into regions with natural periods, here green for short periods and red for long ones. The optimization also solves for a start frame at each pixel. Staggering these start frames greatly improves temporal consistency. The result is a seamless, crisp loop with few blurring or ghosting artifacts. Unlike in a traditional loop, each pixel can have a different looping period. We extend the representation to offer greater runtime control. We first compute a per pixel static frame and activation level. This defines a progressive video loop in which a slider continuously varies the level of dynamism, from a static image to a highly animated scene. We start with a static image and gradually add dynamism as the slider moves to the right. We can also jump to any desired level of dynamism. Here is another example. The user can quickly adjust the level of scene activity depending on personal taste or mood. The representation also allows spatial control over dynamism. Whereas the slider defines a single priority over looping pixels, we can override this by clicking a set of natural regions. These independently looping regions automatically preserve spatial consistency. Here, we start with a static scene and draw a stroke to select regions to activate. Note that the loop remains seamless. In this example, we start with the most dynamic loop and disable animation over the waterfall. A touch interface would be ideal. Similarly, here we freeze the motion of some of the pigeons. Here are some results of automated looping. We have experimented with more than 100 videos. Our optimization is fully automatic, and all results use default parameters. The representation is extremely concise. The looping parameters take less than 100 kilobytes. Only a subset of the input video gets used, so we remap that content into a more compressed video. The final storage is a fraction of the size of the input video. This comparison highlights the benefit of allowing different per pixel start times. With a single start time across all pixels, temporal blurring is much more evident. With the simplest approach, loops with large changes appear early in the progressive video loop. As shown on the right, we modify the cost function so that subtle motions appear before larger ones. The large motion of the foreground flower is delayed, whereas the subtle motion in the mid-range is introduced earlier. In some cases, it would be nice to adapt the default parameter settings based on the content of the video. For large scene motions, spatial seams may be unavoidable. Sometimes the video loop is visually plausible, but semantically incorrect. Here are some more examples of artifacts due to scene motion. Thanks for your interest.